In this video, we consider the detailed mechanism of one specific acyl transfer reaction, namely the conversion of an anhydride to an amide. Okay, so this was one of the examples that I gave on the previous video when we did the overview of the acyl transfer reaction. So in the reaction itself, we have an anhydride, specifically acetic anhydride in this case, reacting with two molecules of diisopropylamine to give N,N-diisopropylacetamide as the amide product, and then the byproducts are diisopropylammonium acetate. Those are basically the byproducts that we don't care about. Okay, so let's look at how this reaction takes place, taking into account the principles that we developed in the last video. So the first step is going to be nucleophilic attack of the amine nitrogen on the carbonyl carbon. Okay, so this is going to need two arrows like all of these carbonyl addition steps do. So one arrow going from the nitrogen lone pair to the carbonyl carbon, and then the second arrow breaking the carbon-oxygen pi bond, putting those electrons onto the oxygen. So the product in this case is very similar to what you get after the first step of imine formation. You have a structure with a nitrogen that still has its hydrogen on it and bears a positive charge, and then the oxygen has a negative charge. This is okay with nitrogen because nitrogen is a good enough nucleophile to react with the neutral carbonyl group. Okay, however, as soon as you form this mechanism, it is going to want to undergo a proton transfer step, because we still have a positively charged nitrogen, and when you're working with amines as your nucleophiles, amines are fundamentally basic molecules, so we're going to treat this reaction more like it's under basic conditions than like it's under acidic conditions. So this is where the second molecule of diisopropylamine comes in. It now acts as a base rather than as a nucleophile and removes the most acidic hydrogen from our intermediate, which is the hydrogen on the nitrogen that's causing it to have a positive charge. Okay, so this is a proton transfer step, two arrows, one from the base to the hydrogen, and then the second one breaking the bond between the hydrogen and the nitrogen, putting those electrons onto the nitrogen and making the nitrogen atom neutral. Okay, so now we just have one negative charge left on the oxygen. And our third step for this mechanism is going to be expulsion of the leaving group to regenerate the carbonyl functional group. Okay, so the leaving group in this case is acetate. So you use the electrons that are on the oxygen with the minus charge, you bring them down to reform the carbonyl CO double bond, and now in this case you have formed a much weaker base than we had prior to this step of the mechanism. You had an RO minus, which is an alkoxide base. The conjugate acid of that would have a pK of about 16, and now we have generated an acetate minus with a conjugate acid pKa of about 5. So this particular step generates a much weaker base. So this is the irreversible step in this mechanism. The first two steps can both be thought of as being reversible and can go in either direction. But this third step is only going to go to the right, and that is going to drive both of the first two equilibria to the right and drive the reaction to completion by Le Chatelier's principle. Okay, so this is an example of an acyl transfer in which we are converting one carboxylic acid into another carboxylic acid derivative, keeping in mind the order of reactivity that I provided for you in the last video. And that order of reactivity is once again explained by having a good leaving group to leave in the final step.